This begins the first major unit of this course, which we use to cover physics as one of the largest big data problems. It also happens to be an area I'm reasonably familiar with, as my PhD is in this area, and I actually used to do physics experiments, which were naturally smaller than this because they were done many years ago, and but they certainly give me a reasonable good overview of what's going on here. So this particular area is got a lot of press because it discovered the Higgs boson, and we will focus on that data. The actual analysis and discussion is valid for the broadly for this type of experiment or this type of scientific research. I should also point out this is one of the so-called largest of the big science areas because everything is done on the most enormous scale, from the accelerator through the teams of people who work together to find results from the accelerator. As always, we have our big data ecosystem using clouds, running data analytics collaboratively. The collaboration is clear in this example here because we have over 3,000 people on a single collaboration analyzing data. Clouds are not so clear because although they are used and clearly work quite well. The analysis for these particular experiments was set up well before clouds were available, and so they have features in common with clouds. They are formally set up as a grid across the world, but they're doing the types of problems that can be well done on clouds. The data will turn out to be clearly big data because we have 15 petabytes per year, and we are solving problems in physics informatics. And here is our usual collage. You will not find physics informatics here. That term is not used, even though it's practiced. It's sort of interesting how some fields always use the term informatics, some sometimes use it, and others, like physics, never use it. Chemistry, for example, does use informatics to describe a lot of the key work between on the IT to support drug discovery. All right. So in this first section, we're going to set the scene of the physics problem and what we have to do, and then as we go through this section, we will see that the key analysis method is not some fancy machine learning algorithm, but rather relatively straightforward, although done with great care, statistics, analyzing the data and using what's called histograms to present the results. And this type of physics experiments gather so-called events, which are things observed which have particular properties, and you group together things with like properties, and that's called a counting experiment. You count how often something happens. In this case here, we're going to be ending up counting how often the Higgs happens by grouping together particle events taken at the accelerator which have Higgs-like characteristics. So this complicated diagram really summarizes the entire sort of physical situation. We have at the top left a picture of the accelerator, which is 175 meters underground, and it has various places marked on it. CMS is one of the experiments, LHCb is another, ATLAS another, and ALICE is another. Otherwise, this just takes protons and antiprotons and whips them around in a circle, gradually building them up to larger and larger energies. Protons, being heavy, do not radiate energy very much, and so you can actually make protons much more energetic than electrons, which are so light they radiate their energy very, very fast if you send them around in a circle. So there is a reference up here, which is to a paper which is published as a chapter in a book which you might want to look at, or else that paper, almost the correct version of that paper, is up online. And you will see that the data is taken at the accelerator. It is immediately analyzed to remove events that are obviously not useful. And then it goes through various stages, increasing in value and decreasing in volume. And this is all done on the so-called computing grid. And as we mentioned later on, the computing grid's about 1/3 of a million cores running simultaneously across the world. In this problem, we take lots and lots of events, and each of those events can be analyzed independently, although we don't actually think of it at the event level, because it takes only maybe 10 seconds to analyze an event. If we worried about every event, we would have lots of overhead. So we tend to do things in bunches of events or files of events, which produce jobs which run for many hours. Still, those jobs which can run for many hours, or each of them can be done independently, and each of those jobs sequentially goes through all the events associated with it. And both grids and clouds can analyze this type of data. And because this whole project was set up almost 15 years ago now, I suspect the first detailed and setup of the software was done. They are using the technologies of that time, which is grids, and not the technologies of the day, which are clouds. And as it's working, there is no need to switch. Whether it's a good idea to switch in principle is sort of irrelevant. You don't take, you spend a huge amount of effort setting it up. You don't throw that effort away. Note that an interesting feature of this whole problem is the huge amount of effort was spent in getting the software to work. This field, like other big science fields, knows that software is very important and data analysis is very important. So all of that was planned and tested many, many years before the first events rolled out of the accelerator. If we now go to the top right, we see an actual picture of one of the experiments, Atlas. There were two sort of major general purpose accelerator experiments, Atlas and CMS. Each of those lives, as is shown in the top left, at a different part of the accelerator where the proton and antiprotons collide. And there's a good reason, as we'll actually discuss a little later in Unit 4 of this section, to have more than one experiment which can tend to probe the same thing, because you're very worried that in something of this complex, look how big this thing is. It's far bigger than the poor old person here. And so the chance of making a mistake and assembling it wrong, and when you assemble it, putting in a bias that gives you the wrong answer is rather, I don't know, it's high because these are done with highly competent people, but it's worrisome. And by doing an analysis on two totally separate apparati is obviously one particularly important way of making certain that the answers are believable. So here it points out that the tunnel, which is shown, effectively shown here in this symbolic picture, which overlays the accelerator underground on a picture of somewhere near Geneva, and crossing actually the France-Switzerland boundary. That's 27 kilometers, 17 miles in circumference. As we mentioned, there's 15 petabytes per year, and exactly that number is sort of a formal number. Maybe it's sometimes half that and sometimes double that, and because they sometimes run the accelerator more often than other times. They improve the accelerator, so they take it down. They switch it off to save electricity and things like that. So, and sometimes it even goes wrong. They have to switch it off to correct the apparatus. And this set of 350,000 cores is called the LHC computing grid, and they're sort of arranged across the world in a three-level structure. We have at the top level CERN, which is the laboratory where this accelerator is situated. That processes some pretty large, maybe 20% of the data. Then we have tier 1, which there's one or more in the major continents. So that there is a tier 1 also for each experiment, and those are national level facilities, and then tier 2 are regional level facilities. Indiana University, where I'm situated, has a tier 2 Atlas computing environment. And then formally tier 3 is sort of the user. So we have host accelerator, national facilities, regional facilities, physicists analyzing the data. And to give this example here of CMS, it had 7 tier 1 and 50 tier 2 facilities. One thing I've not discussed yet is this Higgs event. And so we have these protons and antiprotons colliding head on. And then when they collide, all sorts of disaster happens. They break up into hundreds of particles. And these hundreds of particles are tracked in various ways in this apparatus. The tracking is different depending on the nature of the particles. Some hardly interact. Some interact, but they interact due to their charge. These are the actual tracks you see here. These are charged particles being measured in what they're deposited when they go through chambers and things like that, full of gas that will respond to their passage. Other particles are only seen through the cascades that are produced when they enter into, say, heavy metal. That's something like photons, or which come from either directly from the collision, but more likely from the decays of particles, like the pi zero, which always decays into 2 photons. And so here you see this rich record of the event. Of course, this is just a picture. The actual event is really recorded by the parameters of all these lines. These things here are the energy deposited in so-called calorimeters, which measure these showers produced when particles go into them. So all these experiments consist of they understand very well how the different types of particles interact with matter. They put together a set of devices which record this interaction. They do it over as wide a range as possible, and they are particularly sensitive to do where it's most important. And the most important is sort of around here in the sides, because the particles that go straight when the proton and antiproton collide, most of the activity goes straight forward or straight back in most events, and that's not so interesting. That's the most common events. We're looking at rather uncommon events, those that produced remarkable scientific new particles like the Higgs. Those tend to go off sideways, and that's how I actually detect them. A lot of energy going in directions that the typical event doesn't do anything. Getting rid of all these uninteresting events where nothing much happens is the purpose of the hardware trigger, the actual experimental apparatus, and also a cluster that takes the data immediately from the apparatus and runs it through a filter to remove as many possible of the uninteresting events.